So many thanks for organizing this event. I'm very happy to be here. And many thanks for this invitation. So today I'm going to talk about a recent work with Mohamed Rael and Tony Lelière about the influence of Monte-Carlo sampling on greedy algorithms for reduced basis. So what I'm going to talk about is about some theoretical results that we managed to obtain on these Monte-Carlo samplings that I'm going to tell you about, and about some numerical algorithms that are designed inspired from these theoretical bounds, and what we can say about them. So first of all, I'm going first to recap some well-known results, I guess, to all of you about greedy algorithms in a deterministic setting. Okay, so this will be quite quick. I guess most of you are very familiar with these results I'm going to talk about. And then I switch in the second part of our talk about these greedy algorithms in the stochastic setting. What were the algorithms that we were considering, why we were motivated by this kind of algorithm, and what we can say about that theoretically and from a practical point of view. So let me begin with just some recaps about greedy algorithms in Hilbert spaces in the deterministic case. So first of all, I need to introduce some notation. So here V will denote a Hilbert space, typically of functions, okay? And P here, curly P, will be a subset of parameter values. And typically here, I'm going to assume that it will be a subset of R to the P, okay? So that parameters will be given as P-dimensional vectors here. And for all values of this vector of parameters, mu in P, I'm going to consider U mu to be an element in V, okay? So which will be indexed by the value of these parameters. And what I will denote in the sequel by curly M here will be the set of all these parameter dependent elements of V. So curly M will be U mu for mu belonging to P. And I'm going to assume in the following that it is a compact subset of V. Okay, so an example a lot of you are very familiar with is the following one. Assume, for instance, that for any value of the vector parameter mu, that U mu in V can be identified as a unique solution to some PDE system of the form here, A of U mu mu equals 0, where A of mu is a differential operator depending on the parameter value mu. Then typically the aim of reduced basis methods is to find efficient numerical methods in order to approximate any element U mu in this solution set, okay, by approximating them in a small dimensional linear subspace. Okay, so here I'm going to assume that we are in a very general setting and that U mu may not be given as a solution of a PDE, but think of it as being the typical test, typical situation here. So M is also called the solution manifold very often. So here I will call it the solution set, but it's typically the same object. So as I told you, reduced basis methods, the aim of reduced basis methods is to try to approximate any element of the solution set in a very small dimensional subspace, okay? And the best error that can be achieved is typically measured in terms of this Kolmogorov n-width that most of you are very familiar with. So let me introduce some further notation. If X is a finite dimensional subspace of V, okay, I will denote by pi X the orthogonal projector onto X. And then the n Kolmogorov width of the solution set M in V is defined as the following. For any linear subspaces Vn of V of dimension small n, you can consider the following quantity, which is the supremum over all the parameter values mu of the error between U mu and its orthogonal projection onto a linear subspace Vn. Okay, and you can consider the infimum of this quantity here over all possible n-dimensional subspace. Okay, and so this infimum is denoted by Dn of M indexed by V, and it is called the Kolmogorov n-width. And this quantity typically denotes the best error that you can achieve if you find somehow between inverted commas, an optimal n-dimensional linear subspace that realizes this infimum. Of course, in general, the existence of such an optimal linear subspace is not guaranteed, but it gives some kind of gold standard that one wishes to achieve, at least quasi-optimally, when one wants to approximate, to use this kind of reduced basis method. Okay? And so the question that reduced basis methods try to answer to is the following one. Is it possible to find a constructive way to construct a sequence of linear spaces, xn, each of them being of dimension small n, such that the error that you obtain associated to each of these subspaces xn is close to the optimal error that you can achieve. So more precisely, for a given space subspace xn, if you define this quantity sigma n to be the supremum over all the parameters values in P of the error between u mu and its orthogonal projection on xn, can this quantity be comparable in terms of decay with the dimension n to the Kolmogorov n width of the solution set? And greedy algorithms, which were designed for reduced basis methods, do achieve this kind of properties, as was proved by in a series of work I'm going to mention earlier on. But first, let me explain, recap what is the definition of this greedy algorithm in an ideal setting. First, it is an iterative algorithm which constructs in a constructive way such a sequence of quasi-optimal spaces. So its initialization phase reads as follows. You first select one value of the parameters, mu1, such that mu1 maximizes over the set of parameters values mu, the norm of u mu in V squared, okay? And then you select the first one-dimensional subspace x1, which will be the vectorial space spanned by u mu1, okay? And then as the iterations go on, at iteration n, assuming that you've already constructed the linear space at iteration n-1, which is denoted by x-1, you still proceed by selecting at iteration n the value mu n of the parameter values, which maximizes over all possible mu the error between u mu and its projection onto the n-1 subspace. Okay, so in other words, you select at iteration n the parameter value, which maximizes the error given by the previous subspace that you constructed up to now. Okay, and then you define the next subspace, which will be of dimension n. Xn will be the vectorial space spanned by all the selected functions that you've given by this greedy algorithm, and then we'll read as the span of u mu1 up to u mu n. Okay, so these are ideal greedy algorithms. This is the ideal greedy algorithm, and you can consider relaxed version of these algorithms, which were also analyzed in several works, and which will play an important role in what I'm going to tell in the following. And these are weak greedy algorithms. The weak greedy algorithms depend on the parameter gamma, which is between 0 and 1, so positive and below and smaller or equal to 1. And it reads as follows. At each iteration of the greedy algorithm, the parameter values mu1 up to mu n will be selected so that this condition, which is a weaker condition than the one I've introduced before, is satisfied. For instance, at the initialization step, you're going to require that mu1 is such that the norm of u mu1 in V is greater than gamma times the supremum over all the parameter values mu of the norm of u mu. So this has to compare to this quantity here. So mu1 does not have to be the arg maximizers of the norm of u mu, but just have to satisfy this relaxed condition. And at iteration n, you've got such a similar kind of relaxing the previous condition in the sense that the parameter mu n will be such that the error between u mu n and its orthogonal projection onto the space xn minus 1 will have to be greater than gamma times this supremum here. Okay. And so these are called weak greedy algorithms associated to the value of the parameter gamma. And so it was proved in a series of works, the last of which having been done by Ronald Devor, Petrova, and Wasserstein in 2013. And so it has been proved that indeed such sequences of linear subspaces are quasi-optimal. So here I'm just giving a simplified version of the theorem proved by Devor, Petrova, and Wasserstein. But indeed, what can be proved about this sequence of linear subspaces is that the error that they that they produce in order to approximate the elements of the solution set can be comparable to the Kolmogorov n width, which, remember, is kind of the golden standard. Okay. And in particular, if, for instance, if the Kolmogorov n width decays like n to the minus alpha, to some with some positive exponent alpha, this implies in particular that the error given by the sequence of subspaces given by greedy or weak greedy algorithms also decays like n to the minus alpha. Okay, so that's a nice, very nice feature of these greedy algorithms. And so the principle of reduced basis methods in a deterministic setting is the following. In an offline stage, some values of the parameters mu1 up to mu(n) are selected using a greedy or a weak greedy algorithm. And then in an online stage, any element of the solution set, u mu, for any value of the parameter vector mu in P, is then approximated as the linear combinations of these guys, which are called the snapshots, which are u mu1 up to u mu(n), where mu1, mu(n) are the values of the parameters which have been selected by the weak greedy algorithm. Okay? So this is a context that I guess most of you were familiar with, and this is what is not about greedy algorithms in this deterministic setting. So now let me switch to the stochastic case, sorry, which we were interested in. So first of all, I would like to mention a few works about the study of greedy algorithms in various stochastic settings. So the list is far from being exhaustive. Don't hesitate to come and see me if you see that I didn't mention your own work on this topic. There's definitely things I haven't mentioned here. Okay, but I just would like to mention, put a few highlights. For instance, there have been work by Catherine Smetana, Olivier Zam, and Anthony Partera on the use of randomized residual-based error estimators in the case of reduced basis methods. There have been contributions by Albert Cohen, Wolfgang Dahmen, Ron DeVore, and James Nichols about the use of random training subsets for these greedy algorithms, which are subsets of the parameter value set that can be used at each iteration of this greedy algorithm. And here I'm going, what I'm going to talk about is about a variance reduction method, which was designed by Sebastien Royaval and Tony Lelièvre, using a reduced basis control variate paradigm. And actually what we did, the very first aim was to try to analyze from a mathematical point of view the methods that they had introduced in this paper. I also would like to mention this work by Vidal Codina and Guyenne Gilles and Pereire, where these people designed a multi-level Monte-Carlo method, also using a reduced basis paradigm. And what I'm going to talk about is also related to what they did in this work here. Okay. So let me now give you the context we were studying and explain to you the methods that Sebastien Royaval and Tony Lelièvre has designed. Here G will be a positive integer, and P of RD will denote the set of probability measures on RD. Okay, and I'm going to assume here that Z is a random vector of dimension D, with its law characterized by a probability measure, which will be denoted by nu in my talk. Okay, and I will denote by L2 nu of RD the set of functions U defined over RD with values in R, such that they are square integrable with respect to the measure nu. Yeah.
The probability measures are assumed absolutely continuous with respect to Lebesgue measure, or they can be atomic?
At this point, they can. Later on, they will be assumed to be no, at this point, they can be atomic. And I'll tell you at some point, but I don't use it.
Thank you.
And so you L2 nu will denote a set of functions that are square integrable with respect to nu. And for all nu in P, I will assume that u mu will belong to this space here, L2 nu over RD. Okay. And so that M, the solution set I'm interested in, is a compact subset of L2 nu over RD. Okay. I'm going to make an additional assumption on the solution set. I'm going to assume that any functions here, u mu, have to be continuous over RD. Okay. So then the objective of this work was first to analyze from a mathematical point of view the variance reduction method, which was proposed by Sebastien Royaval and Tony Lelièvre, And their aim was to efficiently compute the expectation of u mu of z, okay, for many values of the vector parameter mu, okay. And they wanted to do that using a control variate paradigm based on a control variate method based on reduced basis. Yeah.
Expectation mu is not random here. The expectation is with respect to
there are
z.
two different objects in there. So z is a random variable, okay, and mu is a parameter.
Parameter is deterministic.
Yeah, somehow the parameter is deterministic, absolutely, and the stochasticity is really encoded in this set variable, absolutely. So somehow we are assuming that there are two different objects. Yes.
So you're saying mu in P is not a set of probability measures.
No, it's the P is
sorry,
using
no, P is really a subset.
misleading.
I should give it another name. But this guy is different. Okay, it's really a parameter value, and it has nothing to do with this P.
Yeah.
Sorry for this. Okay, I need to introduce a few more notation. So here n will be a positive integer, and in the following, set bar will denote a set of random variables, set k, m random variables that are identically and independently distributed according to the law of z. Okay, so according to mu. And here I'm going to introduce these notations that refer to empirical means, empirical variance, and empirical covariance, and which are defined as follows. So for instance, the empirical mean of a function u in L2 nu and continuous associated to the collection of variables z bar will be given as being 1 over m times the sum from k equal 1 to n of u of zk. Okay, and in a similar way, you can define, so this is the empirical mean of u associated to the collection of random variables z bar, and you can define in a similar way empirical covariances and empirical variances. Okay.
There should be no square root.
The variance.
For the very
Sorry, there should be, you're right, there should be no square root. Absolutely. So the standard Monte-Carlo method reads as follows. So you take some a number of samples, mref, that will typically have to be very large, okay? And that bar ref is some collection of IID random vectors of cardinality mref, okay? And so the standard Monte-Carlo method, the most direct one, consists in approximating for every value of the parameter mu into the parameter set, the expectation of u mu of z by its empirical mean associated to the collection of samples z bar ref, okay? And the statistical error given by such a method is typically of the following order. So it will typically scale like some constant divided by the square root of mref, the number of samples taken in your standard Monte Carlo method. So that all in all, for all values of the parameters mu, okay, the computational cost scales like mref, basically, for such a kind of statistical error. Then the idea of Sebastien Moyaval and Tony Lelièvre is the following. The idea was to construct some control variate in order to approximate u mu of z as a linear combination of u mu1 of z and u mu n of z for selected values mu1, mu n of the parameter vectors, which will be selected using some kind of greedy algorithm in the reduced basis method theory. Okay. So assume that the greedy algorithm has already selected such values of parameter, mu1, mu n. The idea of the method is the following. In an offline stage, the expectation of u mu I of z is computed using a very large number of samples. So typically the same collection of variables z bar ref, which I introduced to present you the standard Monte Carlo method. But this is done only for these particular selected values mu1, mu n. Okay, and this is done in an offline stage. Then, in an online stage, you introduce another collection of random variables of cardinality m small, which has the vocation to be much smaller than mref. Okay, and I will denote by z bar small the associated collection of IID random variables, which are still distributed according to the law of Z. Okay, and still in an offline stage, you can compute also empirical expectation of the u mu I associated to this new new samples with smaller size than the reference one. And you can also compute these quantities Aij that are empirical variances of u mu I with u mu j, also associated to the small size samples that you've chosen. Yeah. Yeah.
I'm a bit confused. So, I mean, in the end, you're going to link the Z to the parameters somehow, because otherwise you don't gain anything, no? I mean,
I'm going to check this next slide. Okay. Next slide. So this is done in an offline stage, and then I tell you what is done in an online stage. Yeah.
Yeah, J is quadratic in N, yeah, so you compute them all, yeah. It's,
yeah, so here it's done in an offline stage, but you've got n squared quantities small n squared quantities to compute. Absolutely. But this is done in an offline stage.
yeah, but also the offline costs some.
Yeah, there is an
Offline costs something, yeah.
Yeah, there is an offline cost. Absolutely. There is an offline cost. Yeah.
So in the first bullet point, when you're constructing this approximation of this linear combination, what are the values C? Are they still random or are they realizations?
That's all the point
Same question. Okay, sorry.
Very good question. Answer is going to. So let me ask you a question if I don't answer to it. So let me explain to you the online stage. Once you've computed all this quantity in the offline stage, then on the online stage, for a new value of the parameter vectors mu, okay, you compute empirical covariance of u mu with respect to each of the u mu I associated to the small-sized random samples. Okay. And this goes typically like small n times n small, okay? And then you compute coefficients lambda mu, which is a coefficient of n scalars which I denote by lambda I mu, which are solution to this minimization problem, okay? And actually, it can be shown very easily that lambda mu is solution to this linear problem, where the A matrix I've computed in the offline space appear. Okay, so what is computed in the online space is this vector B and the lambda mu solution of this linear problem here. And then the control variate paradigm consists in approximating the expectation of u mu of Z as follows. So you, as standard in the control variate setting, you use sum from I equal 1 to n. So here, sorry, there is lambda I mu missing. You use sum from I equal 1 to n of lambda I mu u mu I as a control variate to approximate u mu. Okay. And so the expectation of this quantity here is approximated using the small dimensional collection of random variables associated to Z bar small. And these quantities here have been computed in the offline space using the reference random samples, which is of large cardinality. And so these quantities were computed offline, and so there is no need to compute them online either. So here, the cost of computing this thing, in this stage here, typically scales like n small plus n small. Yeah.
Say that these u mu are typically solution to a PDE. I mean, you need to compute them in order to evaluate them at these sample points. There is something in the background here.
Yeah, there may be, but also the typical case that we had in mind is a bit different. Typically, what we're after originally, it doesn't fit exactly this framework. It's a case where u mu were quantities computed out of stochastic processes, depending on parameters. And so indeed, you need to compute. So there you need to compute some trajectories of these parametric random processes. So there is also something in the background. But typically, yes, the idea is that computing u mu of Z is kind of maybe costly. And so, sorry, it's okay. And so here, in terms of computational complexity, this may have an interest in the case when small n times n small is much smaller than mres, okay? And this has an interest if you can achieve similar level of accuracies while small n and n small are in this range of values, okay? And so typically to have a comparable statistical error, you need the variance of these objects here with the lambda mu computed as before to be typically of the order of m small divided by m. Okay, so that motivates why do we need to take this value of these coefficients in order to minimize this quantity here. We want this quantity to be as small as possible for the method to be as efficient as possible.
So maybe I didn't understand it. So you're looking at a problem that has parameters and uncertainty.
Yeah.
You're not modeling the parameters with a probabilistic approach.
No.
So you really think of a problem that has both.
Exactly. So typically what you could imagine is that you want to have some inequality bounds on the one statistical moment of u mu with respect to the random parameters. That's typically the kind of things that
What you could do as well, of course, is you could take the first few KL modes as the first parameters, treat them deterministically, and do the rest of them randomly.
Yeah, but as I said, there is well, in the test case that we had in mind. So typically, what we were interested, so I'm not saying we are there yet, okay? But we were interested in typically computing. Oh, sorry. Right. What we have in mind is that typically we're interested in the solution of such stochastic differential equations, where mu is a parameter which intervenes here into this v mu function. Okay, so it's typically you have to imagine v as being a function for mu will be a function for r and here. And the value of these parameters is difficult to know what should be a reasonable probabilistic law of this kind. Whereas, so here what plays the role of z will be typically the Roman function put here. So, and here there is a natural way to do it. Oh, I'm not saying that this analysis is unable to treat this context. That's exactly what we have in mind. And so here mu, we wanted to have some kind of analysis where mu and z really different forms. Does it answer your question? Mm-hmm. Yeah. Other questions? Okay. And so that's the method that they were Tony Lelièvre and Sebastien Boyaval designed in order to accelerate. And typically, they had this kind of problems in mind. So they looked at so these guys are the overdown Clojure dynamics, so which appears in molecular dynamics. They also had some problems related to option pricing, so which appear in financial applications as well. We have still got this kind of dualities. There are some deterministic parameters entering into some differential, stochastic differential equations. Okay, and so that was their idea. And the whole question is now how to select is mu1, mu_n, and as you expect, that will be selected with the help of some kind of greedy algorithm. Okay. So I need to introduce a few more notation here. So here V, so in reference with the deterministic context I was telling to you in the beginning, will be L2 nu of RD. Will be the set of functions of L2 nu of RD defined up to an additive constant. Okay. And so this is why you've got this quotient notation here. And actually, an important remark is the following. The covariance here defines a scalar product onto the space here. And then dot with a scalar product, then V is a Hilbert space. All right. And so that's typically something that you can do in order to design a greedy algorithm. Okay. So here I'm going to denote, so V will be this particular Hilbert space. The norm of V will be typically the square root of the variance, be given by the square root of the variance. And for any finite dimensional subspace X of V and any element U in V, the X of U will be the orthogonal projection of U in the space V associated to this scalar product and norm. Okay, and it is given as this formula here. Okay.
If closed, yeah, closed subspace, okay.
Yeah, it's closed. Yeah. You can see it equivalently as a set of functions with mean value 0. And so I'm just rewriting here the full ideal greedy algorithm with this notation here. Okay, so it reads as follows. It is exactly the same kind of algorithm as the one I've introduced you in the very beginning of the talk. So you select mu1, mu_n according to this relationships here. Okay, so this is the ideal greedy algorithm that one would like to implement. And so if I just express the norm of V using these variances, it boils down to selecting mu, mu1, mu n according to this relationship here. Of course, the problem here is that in order to compute mu1, mu n selected by this ideal greedy algorithm, one will need to compute exact variances, which we cannot do in practice. Okay, and so in order to alleviate this problem, natural way is to consider, instead of exact variances, to replace them at each iteration of the algorithm by empirical variances associated to some random samples. And so that's why I need to introduce a few more notations. Sorry for that. So for any iteration n of the greedy algorithm, the exact variances will be approximated by empirical variances associated to some random samples, which will be of cardinality mn. Okay, each of these, the collection of these mn ID random vectors used at iteration n of the greedy algorithm will be denoted by z bar n. So it will be a collection of zkn for k being between 1 up to mn. Okay, and these are all assumed to be ID random vectors distributed according to the law of Z. And I'm going to assume here also that the different random samples used at each of the different iterations of the greedy algorithm are also independent from one another. So everything is independently sampled. I'm also going to use some notation from some X finite dimensional subspace of V and any element U in V. The notation here, P bar Xn of U, will be an element of V such that the empirical variance with respect to the collection of samples Z bar n of U minus P bar Xn of U realizes this infimum here. Okay, why? So this roughly plays the role of the orthogonal projection, except that here the exact variances are replaced by empirical variances associated to Z bar n. Here, and I have to say here, there is no guarantee a priori that such an element should be unique. Okay, but there exists at least one. And then the Monte-Carlo greedy algorithm consists in considering the greedy algorithm I just told you before, where all the variances are replaced by these empirical variances associated to the collection of samples Z bar 1 in the first iteration and to the collection of samples Z bar n in the nth iteration. Okay, and so the parameter values mu1, mu n that will be selected will be random variables, which depend on the samples, different samples that are chosen at each iteration of the greedy algorithm, and they will be denoted the following by mu bar 1 and mu bar n. Okay. So now the following natural question arises: is under which assumptions can we guarantee that this Monte-Carlo greedy algorithm still reads as a weak greedy algorithms associated to some parameter gamma between 0 and 1 with some high probability? Okay, and in particular, how should we choose the number of samples used at each iteration of the greedy algorithm so as to guarantee such a property of the Monte-Carlo greedy algorithm, at least theoretically? And for this, so that's the aim of the theoretical results that we get. And in order to prove such estimates, we need to make further assumptions onto the solution set and onto the law of the random variable Z. Okay. Yeah.
Now this is only in one dimension, or
no? This is in this is in D dimension. Yeah, it's also in dimension D. The results I'm going to say will depend on the dimension D.
so it should be integral RD.
RD, yes, absolutely. You're right. There's a D missing. Absolutely. So the first assumption here that we are going to make, that we'll need to make for the analysis to be carried out, is that the probability measure nu has to have some finite exponential moments, or some parameters alpha and beta, so that this quantity here, and indeed this is an RD, has to be finite. Okay. Why do we need such an assumption? It's because we are, for the analysis, we are going to use some results proved by Fournier and Guillain in the 2015 about some concentration inequalities of the empirical measures of mu in Wasserstein distance. And these results, I'm going to tell you what these are about. They are really the backbone of our analysis. So let's assume now that mu indeed satisfies such assumption from now. So what are these concentration inequality I've just told you about that we use in our analysis? They say the following thing. So L, purely L, will be here the set of Lipschitz functions on Rd. And for any Lipschitz functions U, the norm here U, norm L, will denote the Lipschitz constant of U. Okay. So here, phi is some functions defined over R plus star up to R plus star, which has this explicit form here, which depends on the value of the dimension of the random vector D. Okay. So for now, bear with me, phi of k as an explicit expression, the expression of which is not very important for now. So what does the theorem of Fournier-Guillen says? It says the following. Let M be a positive integer and Bz bar be a collection of M ID random vectors that are sampled according to the probability law nu. Okay. And here consider the following quantity, which I denote by T1 of Z bar. And T1 of Z bar is defined as the supremum over all Lipschitz functions with Lipschitz constants lower than 1 of the error between the exact expectation of f of z minus its empirical mean associated to the collection of samples Z bar. Okay, and you take it at absolute value, and you take the supremum of this error of all function f Lipschitz with Lipschitz constant lower than 1. Then the result says that for any error threshold kappa here, which has a vocation to be small at some point, the probability that this quantity here, this supremum, is greater than some kappa will be lower than some constant c times exponential minus c m phi of kappa, where phi of kappa is this function here, and m is the number of samples into Z bar. Okay, so it's quite interesting in the sense that it bounds over a whole infinite dimensional set of functions, the error between the true expectation and its empirical expectation. Okay, and it bounds it in terms of this, in the sense that the probability that this error is greater than some error threshold decays exponentially with respect to the number of samples that you use to compute the empirical expectation. Okay. And so this holds provided the nu satisfies this exponential, finite exponential moment assumptions I told you before. And so that's a very convenient tool for our analysis. And so provided that you make the appropriate assumptions onto the solution set, you can use this concentration inequality in order to get the desired result and the desired estimates. So the needed assumptions are the following ones. You need M to be a compact subset of V. So remember, V is a set of functions that are L2 integrable with respect to nu, up to an additive constant. And I will denote by C2 this supremum here. We're going to assume that M is a subset of L. Okay. And that the supremum over all parameter value mu of the Lipschitz constants of U mu is also a finite quantity, which will be denoted by CL. We also need M to be a subset of bounded functions. And we define this quantity here, C inf t. And also for technical reasons, we need to assume that the Kolmogorov n width of the solution set has to be positive for any n. Okay. And then to tell you the theorem that we are able to prove, and I'll finish the talk there, I need to introduce yet of annotations. So let me go there slowly. Z bar 1 to n denotes the collections of all samples that are used in all the iterations of the greedy algorithms up to the nth iteration. Okay, so it's a collection of Z bar 1 up to Z bar n. Okay, here I need to introduce two different quantities. Sigma bar of n minus 1. It will be the maximum over all parameter values of the error between u mu and its approximate projection u mu, measured in terms of the empirical variance associated to the nth sample set. Okay, so here what appears here, what's important is that what appears here are empirical variances associated to Z bar n. And sigma hat n-1 here is the same kind of error, except that here you use true variances. Okay, so these guys are computable. These guys cannot be computable in practice. Okay, I need to introduce this quantity here. So theta bar 1, theta bar n are the orthogonalized functions that are the output of the greedy algorithm once you use some kind of Gram-Schmidt orthogonalization procedure to obtain an orthogonal basis of the different reduced bases that you've constructed. And so CinfT is the maximum of the LMT bounds of the elements of the solution set. Also these L infinity bounds that you get on the orthogonal vectors that span the different reduced bases. At iteration n. Look, sorry for that. And CNL is the same kind of constant, except that here you measure the maximum Lipschitz constant of the elements of the solution set and of the elements of the orthogonal basis. Okay. And so one needs to define this quantity here, kappa 0, which is defined in terms of this constant and of sigma hat 0 here, and of gamma. Gamma being the parameter of a weak greedy algorithm, which will come about. And kappa n is this quantity here. So I just want to point out here, what is important is that kappa n is indeed a deterministic function of all the samples used up to iteration n. Okay. And then what you can prove using this concentration inequality I told you about is that for any delta between 0 and 1, which has a vocation to be small, and any sequence delta n, each of these delta n between belonging into the subinterval 0, 1, such that the product of 1 minus delta n is greater than 1 minus delta. Okay, so let me take such quantities here. Let us assume that M satisfies the set of assumptions that I've told you about, and U as well, the set of assumptions needed to have this concentration inequality. And let's assume that there exists some parameter gamma such that for all n, Mn, the number of random samples used at the iteration n of the greedy algorithm, satisfy this inequality here. So here, Mn has to be larger than some quantity where this delta n constant comes into play with a log factor. And here you've got 1 over C phi of kappa n-1, where phi is a function appearing the concentration inequality, and kappa n-1 is the quantity I've just defined to you about. Then, so here kappa n-1 can be computed as an output of the n-1 first iterations of the greedy algorithm. So before beginning iteration n, I can compute such a quantity. Okay. And then if the number of samples used at each iteration of the greedy algorithm is chosen according to this inequality, then you can guarantee, using this concentration inequality, that the Monte-Carlo greedy algorithm will be weak greedy algorithm with parameter gamma with probability at least 1 minus delta. Okay. And so this is a theoretical results which kind of give an estimate under the number of samples which have to be used at each iteration of this greedy algorithm to guarantee this property. The problem with these theoretical results is that it gives very pessimistic bounds on the number of samples. So it has a merit of the existing, okay, but it gives very pessimistic bounds. So that's the reason why we developed a heuristic Monte-Carlo algorithm for which there is no theoretical guarantee, but which seems to work in practice on the examples that we tried on. I'm not going to talk about it for the sake of time. So just to summarize what I presented you, we proved some theoretical bounds onto the number of Monte-Carlo samples that has to be used and greedy algorithms so as to ensure, at least theoretically, that the obtained Monte-Carlo greedy algorithms remains a weak greedy algorithm with high probability. And we developed some heuristic algorithm to adapt this number of samples in a more efficient way, but with no theoretical guarantee. And there are lots of open questions that remain there. Can we improve these pessimistic theoretical bounds? Okay. Can we use more efficient sampling schemes such as independent uniform sampling, which we studied there? Could we design some efficient multi-level or multi-fidelity Monte-Carlo greedy algorithm out of this kind of approach? And here, related to what I was telling to you about, that has to be a finite dimensional vector there. Okay. Otherwise, this concentration inequalities, we don't know if there exists such kind of results. I guess it does not exist. And here, what we were after, so what I'm told you about does not fit into this framework, where here the random variable is typically the Brownline motion, which is an infinite dimensional object. So with this, I'm done, and I thank you for your attention.